Hello guys and welcome to my YouTube channel. In this video we'll be continuing our discussion for the 2024 USEMO which was held this year. In the previous video we discussed problem 1 which was a nice and easy combinatorics question. In this video we'll be discussing problem 2 which is a number theory question. So what are you waiting for? Let's get started. Alright, for problem 2, we've got a number theory question. So we're given that k is some positive integer, and we're given 4 that's points, basically, x, xi, yi, and they are telling us that the LCM of each pair is equal to k. So the LCM of x1, y1 is equal to LCM of x2, y2, and so on, and it's equal to k. And they are telling us that these vertices, these 4 points, they form a rectangle, non-degenerate rectangle, and we need to show that x1, x2, x3, x4, this product is a perfect square. Okay, so let's first of all analyze all our conditions and translate them basically to some equations. First of all, they're telling us that these form a rectangle, so let's see what does that mean. So if you have like a rectangle, what do you know about it? If you know the coordinates of these points. Well, first of all, the easiest and very standard thing is you know that this is a parallelogram, right? And you know that means that the coordinates of this plus this is equal to the coordinates of this plus this. This is a very standard one. That's the same as saying this vector here is the same as this vector. So this immediately gives you some easy equations that are, for example, x1 plus x3 is equal to x2 plus x4. And you also know that y1 plus y3 is equal to y2 plus y4. As I said, you can just say that this vector x1 minus x2 and is equal to x4 minus x3. It's equal to this. Okay, now we already have these two. But this is not enough because this only represents a parallelogram. It doesn't represent a rectangle. So we need something else for a rectangle. So what is something special about rectangle that the parallelogram doesn't have? You can do it in using many ideas. Maybe you can say this is 90 degrees, like perpendicularity here. But what we'll be doing here is the diagonals are equal, right, in length. So you can just say that the length of this, use the distance formula to say this thing is equal to this thing, and hence we can just create this x1 minus x3 squared plus y1 minus y3 squared is equal to x2 minus x4 squared plus y2 minus y4 squared. And now you can just expand everything. Here you're going to get x1 squared plus x3 squared plus y1 squared plus y3 squared minus 2 x1 x3 minus 2 y1 y3, and it's equal to the same thing here. But of course you should not keep just looking at this. You should try to simplify this, because remember we know these two. So how can you simplify this? Well, easily. You can just take these guys here and square them. If you square them and then add them, you're going to also get here the same part here, x1 squared plus x2 squared plus y1 squared plus y3 squared, and here the same thing. So you can actually then subtract them. Of course here you're going to get 2x1 x3, and here you already have minus 2x1 x3. So when you subtract them, you're going to get just these as a sum. So you're just going to get after that x1 x3 plus y1 y3 is equal to x2 x4 plus y2 y4. That's perfect. So right now we have these two and you have this. If you combine these three together, then for sure we have satisfied this condition, the rectangle condition. So we can now ignore it. Alright, so let's try these equations. Equation 1. By the way, remember that the question is asking us to show that this is a perfect square. You can see that the question is like not symmetric, so for sure we can actually show that y1, y2, y3, y4 is also a perfect square as well. Anyway, this thing links the x's. We also have this that links the y's as well. Sorry, plus, and we have this to link the like x's with y's. What we can do here is we can just shift like the x alone and y separate the x and y's, because we'll be just working with the x, right? So probably it's a good idea. Is equal to y2, y4 minus y1, y3. Okay, so we have these three. Let's give them numbers. Okay, very nice. Now, next step, remember that the LCM is of all the numbers is k. The LCM is k. So we know that all these numbers are divisors of k, right? Very nice. And if we just remember that what's the question is asking us, show that x1, x2, x3, x4 is perfect square. So we need to show that this product is something like m square, right? Something like perfect square. So how exactly can we show that the product is a perfect square? Well, one idea here, since you have like this big product, the idea is very simple. You can just take a look at one prime number, like a prime p, and look at the exponents or the VP of each one of these, like the x1, x2, x3, x4. Each one is going to have p to the something, right? Like x1 is p to the something, x2 is p to the something, and so on. So if these add up to an even number, then that's it, like we're done. If we can show for any prime p the VP of x1 plus the VP of x2 plus the VP of x3 plus the VP of x4, it's an even number divisible by 2, then yeah, we're done. So this is exactly what we'll be doing here. So our goal is to show that VP x1, or generally speaking, the VP of xi sigma is even. This thing is even. Okay, very nice. Of course, if you remember, since we're working with some prime p, then we already know that, like, from the fact that the LCM is k. Let's say k itself has k is equal to p to the m times like some stuff. So let's say that the VP of k is equal to m. So assume VP k is equal to m. This is like m basically. And what we know right now, that we know that the VP of xi and the VP of yi, like one of them, or the maximum actually, is equal to m, right? This is true for all like 1, 2, 3, 4, 1, 2, 3, and 4. Because we know that like if we take x1, y1, the LCM is going to be k, right? So if this thing has p to the something and this thing has p to the something, the max of these two is going to be m itself, right? Which is the power of like p in k. So yeah, basically this is like very important thing to keep in mind. Let's keep this in our mind. Okay. So in fact, we kind of know these guys. Many of them are m, but those that are not m have the y's, like the VP of y's is actually m. So yeah, keep that in mind. Either like VP of x is m or the VP of y is m. So now we can just kind of discuss some cases. Of course, the first case you can take a look at is what if all the numbers, all of the x's have like the VP of x1 is the VP of like x2 the same as 3, the same as 4, that's like they're all equal to m. If they're all equal to m, then actually we're done, because that means this thing here is just 4 times m. 4 times m is even, so we're done. So the first case is actually easy if all of them are the same. So now the second case is if we have three of them are the same. So now this case, let's like say cases. So case 1 is if like all of them are basically m's. VP of x1, VP of x4 equal to m. This one is really easy. Now case 2, if only three of them, let's say like without loss of generality that maybe x1, like x2 and x4, x3, they're like all m. Same thing here. But like the fourth is not maybe. Then if we look here, we need to use one of our equations, right? If you look actually in this equation, because probably it's the most useful here, since we already know about these, but we don't know about 4. If you look at it, at this thing is going to have p to the m times something. This thing, p to the m times something, p to the n times something. So that means that this thing must be divisible by p to the m. But can it have something greater, like p to the m plus 1? Of course no. Because remember, we know the max is m. So the rest, if this thing was not m, it's going to be less than m, strictly less than m. So a contradiction. So that means like this must be m. So in fact, if three of these are m, the fourth is already m as well. So you can actually like mix these two cases in one case. You can say case 1, if like 3 of the x's, the xi, have VP xi is m. Then the third, the fourth, like we have four of them. Like the fourth, let's say, has also VP equals to m. So that means, of course, we're done in this case. Okay, so now case 2. Okay, 3, 4, we're done. What if we have 2? 2, the xi only, like they have VP xi equals m. So the other two don't have like VP as m. So that means their y's like are going to be like the m's. So now we have some, of course, cases, because they're either like x1 and x2, or they are x1, x3. The rest actually are the same, right? Because if x1 is like and x2, it's the same as saying x2, x3. You can like see the symmetry here. We have a symmetry, right? Oh, sorry, actually here we messed up. It's 3, and here it's 2. Here is 3, here is 2. My bad. Like here I wrote it correctly, here I wrote it wrongly. Let me see. Did I mess up here? No, here it's correct. Okay, yeah. So of course it didn't affect anything. We still like have in the case 1 it still works. Anyway, right now in our case 2, as we said, we have a symmetry here. So if x1, x2 like works, then also x2, x3 the same as thing as x3, x4, same as x4, x1. We have a symmetry here. So like in this case, we can just discuss, let's say, x1, x2. In the other case, if they are not consecutive, x1, x2, then like they are x1, x3, x1, x3, or x2, x4, that's the same. So yeah, we can either like just discuss these two cases, either this or this. So let's handle first of all this case. If these guys are m, x1, x2, then of course we know, as we said, that y, in this case, we know y3 and y4 are like all of them are like have VP m. Okay, let's have a look at this. We know x1, we know x2. These have p to the m inside them. What we can look at like as well is this thing here. x1 has p to the m, and x2 has p to the m as well, right? Okay, how exactly can we try to discuss this case? Cannot immediately here. it seems kill it using the getting the fourth one, because we just have two numbers here. Okay, let's try just to move stuff, isolate them. So we have x1 and x2 is equal to x4 minus x3. We know that this here have like p to the m, and this thing has p to the m as well. So it has p to the m divides x4 minus x3. You can say that much. Now x4 itself and x3 itself, it's not p to the m, it's p to the something, right? So these guys are going to give us p to the something, and this is p to the something. And we can take p to the what? P to the minimum, right? The GCD of that. So p to the minimum. So it's going to give us p to the, let's say, k. And the subtraction, one of the numbers is going to be a multiple of p, the other is no. So that means this thing here, it's not going to be divisible by p. Unless, of course, they're equal. They have the same VP. So we have these two cases. Either they have the same VP or they don't. If they don't, then this thing is now co-prime with p. So this thing is just p to the k. But remember, we know p to the m divides this. So k is greater than m. But wait a minute, we know that k is less than m. It cannot be greater than m. It's in fact at most m. So that means k equals m. If k equals m, then actually these both of these numbers have p to the m. So that just gives us the case 1, right? Which is a contradiction, because we're assuming that no, like only two of them. So that doesn't work. So yeah, if they don't have the same thing, they don't share the same p, that will not work. So that same, that means that they both share exactly the same power, like VP. So x4 and x3 have the same VP. So VP x4 equals VP x3. And as we said, we already like know what's x1. It's equal to x2 equals m. In fact, do we need to discuss this case any further? We don't actually, because like take a look at the sigma now. Like this is 2m, and this is 2 times something, right? So it's already even. So actually, yeah, we're done. We handled this case. So very nice. So we already handled this case. Now we need to look at this. The other case, x1, x3. Let's have a look at it. x1, x3. Okay, so they are already isolated. Let's try to apply the same strategy. x1 plus x3 here, x2 plus x4. So we know that pm divide x2 plus x4. Can we do the same strategy? Sure, why not? Just take like p to the k, and now we have like a sum instead of a minus, but that doesn't matter because we can exactly apply the same strategy again. Like either they have the same or they don't have the same. If they don't have the same, then k must be m, which is a contradiction, or that means they should be the same, but if they are the same, then yeah, we're done, it's already even. So that means case 2 is handled. Nice. Now we have case 3. So what's case 3? Case 3, okay, so far we discussed 4, 3, 2. Now, like 1 or 0, right? Or 0 of them, of like xi's, have their VP as like m. Now, if we have 0 of them, like or 1 of them, both of these we haven't discussed them yet. So let's now have a look here. Of course, if we know that 1 or 0, then what do we know? We know that the other y's, they have the VP as m. So now, like we have, like in this case, we have 3 y's that have their VP as m, and here in this case we have 4 of them that they have their VP as m. Okay, but remember what we said. If we know that 3 of them, 3 of the xi have VP m, then the 4th one is as well, right? So that means these two gives us that the 4 y's, like we know that the VP of the yi is equal to m for all of the i's. So in case 3, we know that all of the y's have m as their VP. Yeah, all of these guys have like VP as m. So now this thing is like trash, and this thing is trash because we cannot really use it that much. So probably we should be looking at equation 3. Okay, let's look at equation 3. let's look at the y's, because all of them have m, right? So this thing is going to give us p to the m, so p to the 2m, and this thing p to the 2m as well. So we're going to get p to the 2m as a common factor. So we know that p to the 2m divides this thing here. Let's have a look at it. Let's write it here. Divides x1, x3 minus x2, x4. Can we get something nice from this? Again, remember that each one of this, if this is going to give us some p to the something, right? So this is going to give us p to the something, p to the something, p to the something, p to the something. And we're going to get p to the, like the smallest one, it's going to get outside, p to the k. In fact, like let's say it's a sum of two numbers k. And we're going to have minus something and something. And these two, again, they're going to, like we have two cases here. Either they don't have the same VP, so that means this thing is coprime with P, or they have the same VP. In the latter case, if they have the same VP, that means VP x1, x3 is equal to VP x2, x4. You can see that we're done here, because like you know the VP function, you can just say VP x1, x3 is the VP of x1 plus VP of x3. This thing is VP of x2 plus VP of x4. So their sigma, their sum, is going to be even, right? Because it's just 2 times something. So yeah, in this case, we don't need to discuss it. So let's say that they are not the same. If they are not the same, then this thing is coprime. It's coprime with P to the like 2m. Sorry, with P I mean general. And anyway, we just have here P to the k. If you look at it, P to the k, right now, it's going to be greater than 2m, right? Greater than 2m. So that means that k is greater than 2m. K is greater than 2m. What does that mean? If you think about it, k was sum of two numbers, right? Sum of two VPs. But we know that each one of them is less than m, less than or equal to m. So how could like the sum of them be greater than 2m? That only happens when k itself is 2m. And that means this guy here is m, this guy here is m, which leads us to this case. Sorry, the case 2. So yeah, it's a contradiction here, because like case 2 like actually works, right? And we're assuming here that only one of them like or 0 work. So that means that we discussed this case as well. So in total, we discussed all the cases that are needed, and in all of them we have indeed the product is perfect square, and we're done. Again, what we did here was simple. We just expressed the rectangle condition easily. This one is really standard, and this one is standard as well. Very easy to get it. So we just wrote our equations to get rid of the rectangle condition. Next, of course, we know the LCM is k. But how can we show that this thing is a perfect square? Very standard idea. Just catch a prime at work with the VPs. We catch a prime P and we work with the VPs. This is our goal. This is our goal, to show that the sum is even. And we know this is our condition for the LCM. So we just discussed some cases, right? Bash some cases. So case 1, only 3. Of course, if we know 4 of them, that was very easy. But in fact, if we have 3, then we already have the 4th. So that was very easy from equation number 1. The case 2, if 2 of them, exactly 2 of xi, have the VP as m, we had 2 cases to discuss, but also equation 1 killed them. This is a very actually standard idea. It's very important to keep it in mind whenever you're working with like a sum of 2 numbers, or like subtraction of 2 numbers, that's the same, and you're looking at the VP. You should know this. You only look at the minimum one, right? The minimal one, because each one of them is going to give you p to the something, p to the something. You take the minimal one, and then you're going to get a number remaining that is coprime with p, unless they're like, if you take like, but both of them have exactly the same VP, right? At that case, maybe when you take p to the something from both of them, the subtraction or the addition, like remaining, is going to be divisible by p as well. But of course, that was to our advantage here. Anyway, that was case 2. Case 3, like we worked, you see, as you can see with the y's, actually here, we used the same technique. And in fact, it immediately worked with equation number 3. We exactly did the same idea, but here, not on this. Okay, so that was also in my opinion, not very difficult, like for problem 2. So yeah, that was problem 2. As a summary, this question was really a nice one. What we did here was, first of all, translate the rectangle condition into 3 equations. And then, in order to show this thing is a perfect square, the product, we just quote some prime p, and we try to find the VP of each of these. And our goal was to show it's even, the sum is even. We did that by like translating the other condition, the LCM condition, into this right here, and we use that to discuss basically some cases. So case 1, if 3 of them have the like VP as M, then the fourth one as well from equation 1. Like otherwise, case 2, if only 2 of them have like VP, their VP is M, then we just use the equation 1 again. We follow that idea, which is really powerful idea. As we said, like you just catch the minimum one of them, the minimal one, and you have 2 cases. Either they are basically both equal, their VP, or they are not. And we discussed the 2 cases, and in both of them it worked. Finally, for case 3, where only 1 or 0 of them have VP as M, we move to the Y's because we have 3 of them, so we have actually 4. And we instead use this equation number 3, using like a similar argument. So yeah, that was basically like problem 2. In my opinion, it's not a very hard question. It's kind of medium. Let me know like in the comments, what do you think about this question? And of course, in the next video, we'll be discussing problem 3, which is like the hardest problem of day 1. So I hope you guys are excited for next video. Don't forget to like, share, and subscribe to the channel, and share this video with your friends. And see you guys in the next video.